All right, good afternoon, everybody. Welcome to the last session of the day. Thanks for coming to my talk. So today, before I get started, I just want to dispel any rumors that I'm any kind of distributed systems expert. I'm not. What I'm going to tell you today is more of a story about how we did Akka.NET into production and how many times we failed, as well as how we failed ourselves into actually making $2 or $3 million more than we did when we didn't actually have Akka.NET. So, and all this stuff is in retrospect, so forgive me if there's a few little details that I might have missed. So, let's start from the beginning. So, I am actually from Australia. Forgive the American accent. And I work for a company called Domain, and Domain is responsible for both commercial and residential property on their website. So that's everything from renting, from buying and selling, anything to do with real estate. So one of the problems that we had when we first did this is that Domain had a massive problem with ClickStream Analytics. Does anybody know what ClickStream Analytics is? Well, yeah, there's like one person, but if you don't know what ClickStream Analytics is, it's like Google Analytics. We want to know what our users are actually doing on our website. So whenever you go on a site like eBay, or you click on something, or you send an inquiry that says, hey, I'm interested in this product, eBay actually tracks what you do in the same way Google does. For us, we had a system that did this, but it didn't really quite scale to what we wanted it to do. In fact, it was losing messages, and it was making us look very, very bad because there's no way we could track whether or not it was doing what it was supposed to do. The setup was, it was modern for 2005. The problem was it was getting long in the tooth because we had a system that was basically running on SQL Server. Our scale was, back in 2005, 2007, we didn't have that many users though, but when you fast forward to today, when we have several million users hitting the site, and with ClickStream Events, one of the things that we use it for is the ability to track whether or not the features that we push into production are effective or not. Our product team also uses the metrics to determine whether the things we feature flag are things that we should keep. So for example, we feature flag things of 20, 30, 40%. If we find that the metrics are very low, we ramp it down, and if things get better, we ramp it up. Unfortunately, with this kind of system, it wasn't scaling because we had SQL Server, we had reporting services. It didn't really do much at this point, and it wasn't reliable, and there's quite a few things that we needed to solve. So the first thing that we needed to fix is that we had a system that kept going down. There were times where there's quite a few outages. At the same time, in terms of traceability, if you did 100 clicks or we had 1,000 clicks on the website, there's no way to actually reverse engineer it or audit it and figure out whether or not these numbers actually add up to that. At the same time, speed was a massive problem because we'd have something that would take an entire day to calculate, especially when we had hundreds of thousands of users per week hitting our site at any given time. The last bit is really around accuracy, and the problem there is that without that kind of granularity that we would expect by capturing all the events, we basically didn't have much to work with. Obviously, scaling was a big issue because when we were using SQL Server, we were relying on one server to do all the aggregations. And as I said, it would have been fine like 10 years ago, but when our traffic doubles or even triples, being able to calculate this as fast as it comes in is all but impossible. So fast forward a little bit to 2 or 3 years ago, when we moved into Amazon Web Services, we had all of a sudden a brand new set of we had a whole bunch of toys to play with, because now we could have infrastructure on the cheap. It was easy for us to add new servers, but the problem was we didn't know what to do with it at the time. So around the same time, we started playing around with actor systems like Akka.net. Now, for domain, we are primarily a Node and a .NET shop, so we went with Akka.net. Of course, if you have preferences for other systems, you could go with Orleans or the JVM Akka. But what I'm going to talk about today is not really specific to just Akka.net. It's going to cover a lot of the high-level concepts, and you should be able to apply it to any actor system, maybe except Orleans, because they don't have the state machines unless you bake it in. Now, the idea that we came up with is quite simple. So previously, we had a job that would take several hours to process an entire day's worth of ClickStream events. But what if we had some way to cut the jobs down into 86,400 jobs a day that would take 1 second, or basically the equivalent of 1 job per second for the entire day? And that's where Akka was born. I mean, we thought, hey, it solved our problem, because now we've got all this, these actor systems that could do all these parallel computations, and everything would be okay. But the truth was, we were wrong. We were wrong because we didn't actually consider, how do you deal with state? How do you deal with cap theorem? How do you deal with consistency? How do you make sure that you don't run into any inconsistencies, especially when we're in a business where we need to be able to sell online ad space by saying that we get this much traffic? So it was a challenge for us, because when we first presented this to the management, they said, well, we're quite happy with just getting our reports once per day. But the way we sold it was, we have a competitive advantage over everybody else, because when we publish articles on our website, we could tell immediately whether or not it has an effect on a particular property. Whereas a batch system, you'd have to wait until the next day, and all you have is probably like 1 spike in a bar graph. We could break it down by hour, and that was a huge advantage for us, because we could do all these things in real time that you can't do if you just went with SQL Server and SQL Server reporting services. But before I get into the details of how we actually did it, I'm going to talk a little bit about theory. I'm sure everybody's familiar with strong eventual consistency. But just for the sake of completeness, I'm going to go over it. So the idea behind strong eventual consistency is that you have more than one set of nodes. They'll eventually get the same set of updates, but you can't guarantee that they all get them at the same time. But with strong eventual consistency, the idea is that it doesn't matter what order you get them. As long as they get all the pieces, then everything's going to be okay, and they'll both come to the same conclusion. Now, for eventual consistency, or what I like to call weak consistency, that's a bit more tricky, because you have to make sure that the pieces of the puzzle all come in the same order. Otherwise, you might get some strange side effects. For example, if you're editing a document and you've got 2 people editing the same doc, if the order of somebody typing something is different from the other person, then you're going to have a lot of inconsistencies. Fortunately for us, we didn't really run into this scenario, and I'll get to that in a second. Now, I tried to explain this to one of my junior devs once, and the best way I could describe it is the IKEA analogy. So, being in Scandinavia, I don't have to ask you guys how many times you've been to IKEA, but the idea is that I could take 2 people who don't know each other at all, who probably won't even talk to each other, as long as they have all the pieces they they need to assemble the same piece of furniture and the same instructions to do it, no matter, most of the time, as long as they have all the pieces and as long as they have the same set of instructions, they'll be able to come up with the same conclusion independently of each other. And our system was built on just this simple principle. When we have that kind of scenario where we have a consistent algorithm and we can guarantee that all the pieces make it to all the nodes, then all of a sudden it simplifies things. The other thing I'll get into later is that our system is immutable, so you don't have to worry about syncing deletes. In hindsight, what we didn't realize at the time is that we were implementing something called conflict-free replicated data types. Now, it's just a fancy way of saying, if you follow these sets of rules, you will always be consistent. Now, there's some talks out there that have said that CRDTs are just data types, but what we found in practice with stuff in the cloud is that it doesn't necessarily have to be like a code data type. It's more of a pattern that you can implement. Now, as far as CAP goes, in the previous scenarios, what we were doing was we were running with a SQL Server where we had strong immediate consistency. The problem with that is that we didn't need that. We were willing to trade that strong immediate consistency for the ability to scale up and have these computations done in parallel. Unfortunately, you can't really do that with SQL Server without having to maintain a nasty stored proc, which is what a lot of our devs were doing, and that wasn't really helping us. As you can see here with the CAP theorem, if you're not familiar with the CAP theorem, it basically says that you could choose partitioning, availability, or consistency, but that dot right in the middle here is impossible. You can never have it all at once. So what was more important to us than just consistency was this idea that we can have partitions that would have copies of the data, and as long as we had enough copies of the data in those partitions, we can guarantee that we still are consistent, provided that the consistency lies in the algorithms that we're actually pushing out. Now, for CRDTs, they sidestep the CAP theorem. And it sounds like magic, but once we'll get into this, you'll see that there's nothing magical about it. So as I mentioned before, each CRDT has the same merge operation. And the difference between your CRDT and stuff that you normally work with in a relational database is that duplication is a good thing. And the reason why duplication is a good thing is because there's certain operations that you could pull off in a CRDT that eliminate those duplicates. The other reason why it sidesteps the CAP theorem is that since you have copies of all the data on every single one of the nodes, and you have duplication, it basically makes the data available everywhere, or pretty close to everywhere, depending on your level of duplication. Now, there's only 3 operations for a CRDT. So the first one is querying. It's getting the state. That's pretty much, you could make it an API if you really wanted to, or you could just get a copy of it. In our case, the update doesn't really apply to us because we event source everything and we make no deletes. So effectively here, there's no update, so that cuts it down to 2. The most important part that we have is the merge operation. And for CRDTs, there's a few set of rules that you have to follow in order to have an effective merge operation that you never have to worry about conflicts with. So the first thing that it has to do is it has to be commutative. So changing the order doesn't really change the result. You can do it in any order you want. Associative, you could group the data in any order. Everything will still remain the same. Idempotent, I could run it 1,000 times and I'd still get the same result. Now, here's something for the audience. So let's say I have node 1 and node 2, and they've got 2 sets of data. Now, obviously, in the real world, you'd probably have something more complex than numbers, but for now, let's just assume that you needed to merge these two sets of data. Which operator do you think would satisfy all the stuff here? Now, it took us a while to figure this out, though, but it was so simple that when we figured it out, it was, I don't understand why didn't we think of it at the time. It turns out that union is really all you need. So when I have two sets of data, and I want to make sure that I get consistency between two nodes, and I have no deletes, and it's just immutable, all I need to do is do a union, and it eliminates all the duplicates. It also makes sure that all the unique components are there, and I can do what I need to do with it. So when we look at union, if we go through the list, I could say that union is commutative, yes. Changing the order doesn't do the result, change the result. Associative grouping doesn't matter. Idempotent doesn't matter either because you could run it a dozen times. The C# code looks like this. I know this looks really, really simple. Obviously, this is not production code, but conceptually, this is it. And I've got one hash set, A1, and the second one, and the complexity in merging these two is just that one method call. That's it. The other thing that I have to stress is that everything is immutable, at least within what we did. The reason why we chose immutability in this case is that in other CRDTs, you have to keep track of what you've deleted and try to sync that up. They call it tombstoning. We didn't want to have to deal with that. And at the same time, we wanted to do something a bit more reasonable and collect all the events within, say, 90 days. And then once it gets past that 90-day horizon, we just kill off all the events that we've collected for that one day and for all the listings that listing events that we collected on that one day. Now that I've gone over the theory, you're probably wondering, how do we actually store this stuff? Because if we're not deleting anything, then that's a lot of space that we're going to be taking up. So what we did was we've used two different types of backing stores. So you notice that I've actually copied and pasted the slide from the previous one, and it looks exactly the same. The idea here is that, let's call node 1 Elasticsearch. Node 2 is S3. The point here is that it could be any data source, and as long as you follow these rules, you get the same level of consistency that you would expect. It's almost like magic, but it's not. The next question you might ask is, what do you do in this case? Because this is just numbers. I mean, you can't, most of our data is going to be plain old C# or plain old Java objects, so it doesn't really make sense just to reduce things down to a number, or does it? Because it turns out that there's a way you could actually make sure that you've got a unique hash set for every single piece of data that you have. Now, don't mind the SHA-1, because I do realize that there was a security breach quite a few months back. But the important thing here is that this is a sample ClickStream event. Now, what we've done is we take the SHA-1 hash, or any hash code with a sizable key space, so that we don't get collisions. And what we do is convert it into a single hash string, so that effectively, when we do that kind of merging, it's just like working with very, very large strings or ints. And it works out really, really well. The other thing that we're doing is that this is a logical representation of our ClickStream pipeline. Obviously, it's not to scale, but what we do is that when we have ClickStream events that come in here, it goes straight to the web server. The web server posts the events to Akka.net. Akka.net processes it and sends a copy of the ClickStream event to S3, as well as Elasticsearch. You might also notice that there's a reconciliation process, and that's part of the unioning, but this is at a much larger scale. What's important here is that in this flow of events, we have multiple actor systems working inside of AWS to make sure that everything is consistent and they're always running almost in real time. So for us, I know real time is a relative term, but when it comes to property agents, they always think in terms of days. So when we tell them something is less than 30 seconds, they think it's the most amazing thing ever. And to some extent, it is. Now, if you're not familiar with actor systems, an actor system is a collection of actors, and an actor is essentially a degenerate thread with, it's a single-threaded process inside of an actor system that is guaranteed never to have any kind of locks or conflicts with global or mutable data at all. And the reason behind that is that the messages that are sent to every single actor are immutable. You can't change it. They're built in such a way that they context switch between actors, and you could treat every single actor as a single-threaded process where you don't have to worry about anything. The interesting part about all this stuff is all the systems that we were able to put together as a result of working and failing many, many times over. I remember trying to do persistence in Postgres and trying to get Postgres to do the calculations. It took us a good 1 week because no matter how many instances we would add to that server, what would happen is that the computation or real-time computation was the bottleneck. So what we did was we started fanning this out to Elasticsearch because Elasticsearch has this unique ability to keep adding more and more servers the harder we hit it. At the same time, we came up with quite a few patterns that make a lot of sense so that we get the resiliency that we need so you don't really see any outages. The other obvious use that we have is aggregation. So in our case, it's just a sum or a count. But what we've learned from that is that it's not as simple as it sounds given the amount of traffic that we get in. If we've got 1,000 messages coming in per second, how do you guarantee that there's only less than 10-second lag between the point somebody does something and then the report and the numbers are updated? The most interesting thing that we came up with, at least in terms of the circuit breaking, is the ability for an actor system to detect if certain things have gone offline. So what we would do is if we had two parallel server APIs, one was a backup, we would put an actor system in front of it, and if we detected that if anything went down with any one of those two APIs, it would smoothly cut over and prevent any kind of outage. So one of the things that was, as you can see here, typically we're working on the scale of anywhere from 10 to 20 EC2 instances with multiple actor systems per box. The interesting part about this is that when you go through the Akka.NET docs, they talk a lot about cluster, but we didn't actually use cluster. We didn't even use Akka.remoting. The reason why is that we had a continuous deployment infrastructure, so we were running Octopus deploy, and when we deployed these actor systems to one box, they acted as a single actor in isolation, but they were all linked together by SQS. The interesting part about connecting all these actors through SQS that we never really predicted was this idea that effectively we were creating a distributed swarm. Now the reason why it's a distributed swarm is because SQS has this unique ability to make messages invisible for a short period of time when an actor pulls something off the queue, or in this case, you make a standard HTTP call. It makes it invisible for, say, 5 minutes. And then if the message isn't deleted, it shows up on the queue again. Now, that sounds pretty simple, but the interesting side effect for us is that it turns SQS into a blind dispatch. Effectively, we were running a grid with no master node. The cool thing about this is, what do you think happens if an actor pulls a message off of SQS, and for some reason the actor fails? What happens to the message? And let's say, for the sake of it, I've got 3 actor systems running in parallel on different machines. The interesting thing about this is if the message is not deleted by the actor, it just gets picked up again by another actor. And if that actor is successful, it just deletes the message off the queue and it keeps going. So what we are actually getting here is the ability to have one actor pick up right after the other, even if several actor systems fail. However, as I said in the beginning, we failed quite a few times. And one of the ways we actually failed is that we started getting throttled by SQS. So, as you can see here, the idea was that the more infrastructure we threw at the problem, or at least we thought it was like that, the more infrastructure we threw at the problem, the more we would solve it. But as somebody asked in one of the other talks, he said, well, that's great, you got Akka.net, but how do you handle the cases where you might hit a service too hard? You're always going to run into that problem of, well, that's great, I've got a couple 100,000 actors, but if AWS only takes a certain amount of bandwidth and you're running on one of the fastest servers, then what do you do? So one of the things that we came up with in this case was this idea of throttling. And if you want to learn how to actually do this kind of throttling, it's actually quite simple. Because in Akka.net, it has a timer. This timer allows, it's actually called a scheduler, but this scheduler allows you to send the same message over and over and over again. In our case, what we were doing was we were sending the same message to monitor the amount of memory that we were actually using. Or in some cases, we were checking the amount of SQS messages that we're polling. And if it reached over a certain level, what we would do is throttle down the actor system, or at least one of them, in response to the memory being used. So this is an actual message from production. And as you might have noticed, this is a Slack message. So our actor systems call home. They actually say, I have used this much memory, and here are all the thresholds. What we did in this case is if it reaches a critical threshold, it'll stop the polling or reduce it to a level where, although it'll paralyze one actor system, since we all have them running as competing consumers off an SQS queue, it effectively means that we have this elastic swarm that could keep going even if some of the nodes are in a state where they're critical. So there's some really, really interesting stuff that we came up with, and it really helped us when we ran into these situations where we had a catastrophic failure. So what happened, I think it was almost last year, there was an AWS outage in Sydney. And what happened was it took out an entire region, and we almost lost a lot of data. And how we recovered from it was essentially, we had 2 copies of the data in place. We used this reconciliation process that I talked about before, and on a much larger scale, all we did was take the list of hash codes, which is basically the list of events on one side for S3, and the list of hash codes for Elasticsearch, and we found out where the holes were, and we patched them. It took us quite a few days, but we were able to recover everything. The best part about this is that we run this process every single day, so if there's any problems, we can keep patching it as time goes by, because we operated on the assumption that no matter how good the system we built is, we're always going to have drop packets. You're always going to have partitions, and you're always going to have problems. So we always need to be in that state where we're constantly reconciling the data. The last thing that we did to make sure that we got past this whole thing around eventual consistency is that since we were running immutable, we did one last batch request for all the listings that were affected. So we'd send out the request towards the end of the day, and since we knew that nothing will change at that point, we could send out one more request, and it would aggregate everything, and that would give us the final consistency that we needed. Again, I have to stress this, there's nothing magical here. You could do this on your own backing store. It doesn't have to be S3, it doesn't have to be elastic. The important thing here is that you don't necessarily have this same type of data sources. So I don't recommend doing 2 relationals or 2 elastic searches. We chose S3, by the way, because most of the time it's up, and Elasticsearch was good because we could search the aggregations once we've done them, and you can't necessarily do that with S3. So in hindsight, there's a lot of things we could have done better, but we're pretty happy with the result. I mean, at the end of the day, this project was about adding value to the business, and you can't necessarily do that if we were just going to sit there and tinker and try to build more stuff with it. What happened towards the end of the project, and it's still going, but we're nearing the end, is that for the first time, agents started to trust us, because if we were on the phone with a real estate agent and they said, well, how do I know your numbers are correct? And that's a common thing with reporting. They say, well, how do I know you're not making this stuff up? And the story goes that the customer service rep just told them, well, why don't you just click a few things 5 times and see if it goes up? And it did. And it's these kinds of situations where real time really makes a difference. There's a few other things that we've done, as you can see here, but the lesson learned here is that if you use CRDTs properly and you add duplication, you basically could do this without much effort, because duplication, at least within this context, basically saved our ass. The other thing to remember is with strong eventual consistency, you could achieve that with just using these hash sets, provided that you have a good hashing algorithm. I recommend anything over 128 bits, so you don't run into any collisions. If you can afford the computation, then I recommend going up even higher than that. The other thing that we did use that prevents any kind of outage is SQS. So what happened, since we had so many queues all over the place, if a service went down, nobody would notice. In fact, it wasn't even a Sev 1, Sev 2, it was a Sev 3. You could just hit a button, redeploy, and nobody would notice the difference. And the reason why that was happening was agents were still expecting us to do these kinds of reports or crunch these numbers within a day. So if we had a service go out for 10 or 20 minutes, we just redeploy and everything would be all right. If you were to go with an online service where you would hit a server like SQL Server and ask for a computation, you'd be sitting there for a long time and it would look like the report never came back. And that's what happens with your typical SQL Server reporting service. You send a query out, and then you cross your fingers and hope it comes back within a minute, but it doesn't. So what we learned is that it's a hat trick, but what we did was we did an offline calculation, and to the user, since it was constantly being updated, the result was it looks like it was done in real time. But by the time they were asking for it, the computation was already done. So with that, there's a lot of other stories that come with this, though, but I'm pretty much open to any questions because I realize that there's quite a few other talks that talk about the intro to ACA, but we've covered a lot of cases of how do we actually do this in production, how do you scale it up. So that's it for me. Any questions? Okay, I'll take that as a Norwegian yes. All right, well, thanks for coming.